Welcome back to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we're going to explain fiber orientation. In this study, we're going to ask ourselves, why do we actually study fiber orientation? We're going to discuss the impact of the anisotropic modulus distribution on the final part. And finally, we're going to use the interpretation tools in Moldex3D to interpret the fiber orientation. So first of all, why do we use fiber reinforced polymers? So there's two main reasons for it. First of all, whereas the plastic material without fibers is compressible, the fibers themselves are not. And that actually helps us in two ways. First of all, it gives us better strength. So when we're trying to pull the material along the axis, if the fiber is aligned in that axis, the fiber itself is not able to stretch, whereas the polymer would be able to. So you get actually a much higher strength modulus versus a material that does not have fibers in it. And another main reason for using fiber reinforced polymers is because the material is actually displaced by the fibers themselves. So it actually decreases the weight of the part in addition to increasing the strength of the part. Now there's a bunch of factors that affect the fiber orientation. Really, any of the traditional processing specs, things like injection speed, your temperatures, the amount of pressure that you apply, the geometry itself, and the location of the gate with respect to the part geometry. These can all impact the fiber orientation. But also, in addition to that, the fiber properties themselves, things like the amount of fibers, the length of the fibers, the type of fiber, so what the fiber is actually made out of, the shape of the fibers, which is actually kind of a cool analysis that we can run. We can actually look at the impact of the shape of the fiber, and then the actual matrix of the polymer itself, so how those fibers are interacting with the polymer matrix is extremely important. And there's two ways that we can really run a fiber orientation analysis. You can either do it through a traditional injection molding process, where the pellets will actually have those fibers contained in them. There's also a specialized process where the fibers are actually introduced into the polymer and into the mixture right as the pellets are going from the hopper into the barrel. So that's actually kind of cool. There's a lot of adaptations that have been made in injection molding to facilitate a more controlled fiber orientation scenario. But to control fiber orientation the best, compression molding is definitely the hallmark way to do that. So we actually get a charge that has some sort of preset fiber orientation, and then that charge is simply just pressed into the shape that we want it to be. And that fiber orientation is much more easily controlled. So these two are definitely the leading processes that will allow us to take a look at or to control reasonably how the fibers are oriented in the part and study how the part strength is going to be impacted as well as the part weight. All right, so so when we're talking about fiber orientation, ultimately we're talking about increasing the strength of the material, but that fiber orientation will ultimately also impact the warpage. So what is warpage ultimately? It is a variation in the density that causes an uneven shrinkage in the part, and that uneven shrinkage is where the warpage definition is derived from. If we start out with some sort of density variation, maybe if the fibers are more heavily concentrated in one area of the part, then we'll have an uneven shrinkage, and that uneven shrinkage will cause a warpage at the end of the day. Now, there's a lot of things that actually go into the study of warpage based on fiber orientation, but the overarching concept is that the direction of the fibers is going to impact the ability of the material to shrink back to its original state. So, for example, if we look at this scenario here where all the fibers are aligned in the flow direction, or what we call the principal direction, then those fibers, being as rigid as they are going to inhibit the material from shrinking in that direction. Because, remember, those fibers are rigid, they do not have as high of a shrinkage property, or really any shrinkage property at all, whereas the polymer itself, the polymer matrix, actually does have quite a high shrinkage value with respect to that. So in the fiber orientation direction, you're actually going to get an extremely low shrinkage. You're going to get a low thermal expansion coefficient, but you're also going to get a very high rigidity. As I mentioned earlier, the mechanical properties are going to be much improved because those fibers are rigid. Now, that increase in material properties comes at an expense. Transverse or orthogonal or 90 degrees to that fiber orientation direction, you get the absolute opposite situation occurring. Because the fibers are not aligned in that direction, the fibers are not helping the material to prevent shrinkage. So your material will have a very high shrinkage value and also a high thermal expansion coefficient. And also the material will have a low rigidity. Because the fibers are only rigid in the direction they're oriented, I can pull the polymer essentially just without the fibers themselves. I can pull the polymer and it will have actually a very low mechanical property in that regards. So we really want to be controlling how the fiber orientation is looking like through my part in the particular direction that I'm interested in. So for example, if I know that I'm going to be applying a force in this direction, then obviously I want the fibers to be aligned in that direction. If there's a chance that I'm applying a high force in this direction, maybe the material is being pulled, or maybe a screw is going through this part, or anything, there is a much higher chance that the polymer will crack, or that the part will fail in this direction, whereas it will not fail as much in this direction. Now, in the real molding scenario, unfortunately, there's not really a way to get all of these fibers aligned in the same direction. And the main reason for that is because I'll talk about specifically with injection molding. Through the injection molding process, the fibers themselves will follow along the flow path, and they'll kind of lay up on the surface of the part, but through the thickness of the part, where it really matters, is it's actually going to be quite difficult. But what we end up getting is more of a random orientation, and that random orientation will actually it'll make the rigidity similar in all three directions, but overall the rigidity will be lower. So we want to be, the whole purpose of studying fiber orientation is to be able to control what the directionality of those fibers are going to look like, and that orientation factor is going to directly correlate to the strength of our part. So we see here the difference between isotropic and anisotropic warpage. What this isotropic definition, or what this isotropic word means, is just the uniformity. So if a material is isotropically warping, it means that in all three directions, you can see this is just a cube, so in all three directions it is shrinking exactly the same. Whereas with anisotropic warpage, we actually get a different shrinkage value in two directions from the third direction here. So anisotropic warpage just kind of refers to the fact that not all three directions are the same, whereas isotropic warpage will be. All right, so just kind of harping again on the rigidity of the fiber orientation and the directionality of the fiber orientation. This is a stress strain curve where we have the two extremes. We have one extreme down here where we have completely random orientation, and then we have the other extreme up here where we have perfectly aligned orientation. The slope of this curve is going to be your modulus, which is going to determine the strength of your material. And in a realistic scenario, you're going to be between these two curves in some way or another. There's no way to get high orientation in one direction, and then there's also no way to get perfectly random orientation either. You're always going to lie somewhere in the middle, and that's where simulation can help us out a lot. So what we're doing in the simulation is trying to determine what ultimately is our modulus throughout our part. Now, when it comes to fiber orientation specifically, when we're going to study fiber orientation, we need to be able to visualize what's happening through the thickness of the part. And this is your typical primary direction, or your typical A11 direction, as we call it. And the actual contour of this plot is going to allow you to visualize in general what's happening through the thickness of your part. So in this case, the thickness is normalized across the x-axis, meaning that the 0 value here, or I guess wherever this starts, is going to be at one surface of the part, and then the opposite side here is on the other surface of the opposite surface of the part. So we're looking at this result through the thickness. You can almost flip this 90 degrees so you would get a better conceptualization of what's happening here. And the fiber orientation plot here is divided into three main sections. We have the skin layer, which is right at the surface. So this has almost no thickness at all. You can see that with respect to the entire thickness, the skin layer is extremely thin. We have the shell layer, which is just inside of the skin. And then we have the core layer, which is between the two shells. So we'll have a skin, a shell, a core, and then on the opposite side we'll have another shell and a skin. Now typically in the core, I'll start with the core because it is the largest component to our fiber orientation plot here. The core will typically in the middle have the lowest fiber orientation component in the primary flow direction. And the reason for that is simply because the material, or the polymer, is actually pushing these fibers orthogonal to the direction that the material is flowing. So you can almost think of it like a stick in a stream. The stick is going to apply as much surface area resistance to move along the stream as it possibly can, so it's going to turn sideways. And the fibers will do exactly the same thing. So those fibers are actually turning sideways and being pushed along the flow path with the polymer. And that's why we actually end up getting a very low fiber orientation in the core. But as we get towards the shell, that material is actually, or I should say the fibers themselves are actually getting flipped up and getting pushed up along the sides of the mold. They're getting pushed into the skin layer. Now the skin layer itself will actually have a slightly lower fiber orientation typically. And the reason for that is because the material almost instantly freezes when it hits the mold surface. So whatever the fiber orientation is, when that polymer touches the mold, it's just going to be locked in that fiber orientation. There's not a whole lot we can do to control what actually happens at the skin. And that's actually one of the main factors that we're going to be looking at in a few moments here that simulation is trying to predict, because the fiber orientation on the skin is extremely important to the anisotropic shrinkage properties. I remember anisotropic again from this right here. The anisotropic shrinkage properties are extremely dependent on what happens not only in the core, but also what happens right at the skin of the part as well. The shell layer is going to have the highest fiber orientation typically because polymer is shoving those fibers along the flow path in the middle, but those fibers are actually just laying up against the mold surface as the material begins to cool. So like I mentioned, right at the skin, those fibers are kind of instantly locked where they initially were when the material passed over that region. But inside of that, in the shell, the material is still shearing, and the fibers are able to be manipulated a little bit more as that polymer kind of passes across that shell region. Now, when we're looking at fiber orientation analytically through simulation, there are not only the primary path, there's the transverse path, which is going to be the A22 parameter, and then there's the out of direction or out of plane path, you can almost think of this like the z direction, if you will, or the parting direction. This will be your A33 value. And all three of these curves are going to be important to be able to kind of evaluate what's actually happening through the thickness of our part. But the most important thing is to keep in mind that these three values will always add up to 1. So the fiber orientation component over here on the y-axis is going to be the magnitude of orientation in that particular direction. So like I mentioned, with the A11 curve here, the fiber orientation is going to be very well aligned in the shell region, but very poorly aligned in the core region. The transverse to that is almost going to be completely opposite. So your shell region is going to be very poorly aligned, and where that material was just, or where the fibers were just kind of being pushed along the flow path, that in the transverse to flow, that fiber orientation is actually going to be quite high. And we can use that to our advantage when we're trying to evaluate which way we're going to be pulling this material. We can actually use that to determine where the high strength is going to be. Now, there's a lot of different types of fiber processes out there. When we're talking about injection molding fibers, usually we're talking about short and long fibers. Short fibers usually anything under an aspect ratio of 100. Long fibers usually a little bit over an aspect ratio of 100. When I talk about aspect ratio, I'm just talking about the length of the fiber divided by the diameter of the fiber. So that's what this L over D is. We call it the aspect ratio. So when we're talking about short fibers, usually they're relatively, well, as the name might suggest, they are short. With longer fibers, you have a lot more interesting phenomena, things like fiber breakage. The fibers themselves being so rigid do have some modulus, and that if that modulus is exceeded, then the fibers themselves will break. And injecting those can be quite troublesome sometimes. So we can actually use simulation to evaluate where that material is going to break and what is our final actual fiber length rather than what we started with. Because those fibers, ultimately, when they're going through the barrel, when they're experiencing that shear in the barrel, those fibers will actually break quite easily. Additionally, we have some other advanced processes, things like SMC molding and RTM, resin transfer molding. All of these different types of molding processes are typically going to be done with compression molding. Compression molding just allowing us to either directly control the input fiber orientation, and then the flow of that material, the flow of the material is going to impact the fiber orientation marginally, rather than the flow directly controlling the fiber orientation in injection molding. So compression molding just giving us a lot more consistency over the fiber orientation, but there's a lot of other complexities that are introduced into the compression molding process when it comes to actually either filling out a fiber mat or compressing a fabric sufficiently. Even with unidirectional fibers, those have a lower modulus and can be quite heavily impacted by the compression molding process. So I'm going to be talking primarily about injection molding, although we can do compression molding in Moldex3D. I'm going to be talking primarily about injection molding throughout this session here. Now, for fiber orientation, Moldex3D has developed their own patented anisotropic rotary diffusion model. We call it the IARD, with the I standing for improved anisotropic rotary diffusion model. So the IARD formula just allows us to describe how the fibers are being impacted by the flow. And the mathematics behind the IARD RPR formulation is not necessarily too important, but we really want to understand how each of these terms are impacting the final fiber orientation. So we have three terms. First of all, we have the Jeffreys hydrodynamics, which describes how the fibers are going to be moving along in the actual medium, being the polymer. But then we have two other more complex terms. The first one is the rotary diffusion term. The rotary diffusion term allows us to describe how the fiber is interacting with the other fibers. And it also allows us to study how the fibers is interacting with the matrix being the polymer itself. So we have two parameters, Ci and Cm, that we can control to kind of accurately determine what is the realistic interaction between the fibers and between the polymer and fiber. The Fm, or really I guess it's the retarding principal rate, the fiber matrix interaction coefficient down here, alpha, is going to allow us to control a lot of what's happening right at the surface of the mold. And that's what I mentioned earlier, the fiber orientation right at in that skin layer, right at the surface of the mold, is going to be extremely important to approximate the shrinkage that's going to occur. So again, I'm not going to get too far into this because it does get quite complex quite quickly, but looking at the three different coefficients, we have Ci, Cm, and alpha. Ci allows us to control the shell height. So as we decrease the Ci value, the shell height increases. As we change the Cm, as we increase the Cm, we actually get the slope to decrease, so we can control the height of this shell and the slope of this shell, which can be quite sensitive in the simulation. And then the alpha really just allows us to control the slope transition, really, from our shell region to the skin area. So these three values, or these three parameters, are things that we are constantly studying to be able to accurately predict what the fiber orientation is going to be in the model, and therefore increase the accuracy of the simulation when it comes to the final modulus of the part. And you can use that fiber orientation, you can use that modulus data to continue on to additional simulations and run structural analyses, see when the part is going to fail based on the fiber orientation of the model, based on that modulus distribution. All right, so what I'm going to do is I'm going to go into the filling results. The fiber orientation is going to always be in the filling results. It's also going to be in the packing results as well. You can kind of compare those two if you want to see how the packing actually impacted the fiber orientation. As we are pushing the material, that fiber orientation will marginally change from the filling to the packing. But what I'm going to do is I'm going to go into the filling results, and I'm going to go all the way to the bottom of our filling results where it says fiber, and I'm going to go to fiber orientation. Now, the way that our fiber orientation result here is calculated is based on the three components, the X, Y, and Z components. You can actually go into those and see how those are actually visualized. You can see that these are actually just a color plot, whereas the fiber orientation is a vector plot. And that's actually extremely important to note, because in a color plot, we only get the magnitude. It's very difficult to determine the direction of the fibers from one particular component of the orientation. So, for example, the X direction fiber orientation here tells me that the fibers are very highly oriented in the X direction here, but very low orientation transverse to that. And you'll see that if I go from X to Z, you'll actually see that these colors pretty much just reverse, right? So you get a low orientation here and a high orientation in the Z axis itself. And you should see that pretty often, especially on the surface of the part where the shell is controlling a lot of what's happening. Now, along with a lot of our other results, these are actually solid results that you can slice through. So if I went to result, and I can go to, let's say, clipping, I can actually clip through this model and see how that fiber orientation is changing from the skin layer to the core layer. We can really get an idea of how that fiber orientation is changing over the length of our part in a particular direction. So if I know that I am pulling the material, I'll exit out of here for now. If I know that I'm pulling the material in this direction, or maybe if I'm compressing the part in this direction, I know that the modulus is going to be relatively high because the fibers are highly oriented. However, if I'm going in this direction, then the fibers might not be as oriented. Using this information, I can go to the totalization of these three components, which is going to be the fiber orientation as we were looking at earlier. And like I mentioned, the fiber orientation is a vector plot, which gives us not only the magnitude of the orientation, but also the direction of the fibers. Whereas the direction of the fibers was kind of difficult to evaluate in the X, Y, and Z, the direction of the fibers here are very easily, or very well shown, very obviously shown. Now you'll see that the scale here is actually going from 0.333 to 1. And there's actually a very obvious reason for that. 0.333 means that all three directions have the same orientation. So it means that the fibers are completely random in their orientation. There is no particular directionality to the fiber orientation itself. It's almost like you just have a lighter polymer, and the modulus is not impacted at all by the fiber orientation. This makes sense again because if you remember from one of the previous slides, I mentioned that all three of these components, the X, Y, and Z, or you can think of them more like the primary, transverse, and out of plane, all three of these have to add to 1. So if it's completely random, if there's no particular orientation, all three of those parameters will add to 1. And well, I guess just 1 divided by 3 is 0.333. So so that's where that number comes from. If the fibers are completely aligned, remember this value doesn't necessarily indicate direction. If you want direction, you really have to go and see the individual fibers themselves. But if you see that the material is in a red direction, or in a red color, it means that the fibers are completely aligned in that particular direction on the part. So it means that the other components, so in this case, some of the other components of the fiber orientation, maybe if this is in line with the flow, the transverse to flow and out of plane are going to be extremely low, meaning that the modulus is very high in the flow direction, but in the other two it's going to be actually quite low. So ultimately, when it comes to fiber orientation, the goal is not necessarily to get all of the fibers aligned in the same direction. As I mentioned, if the fibers are all in one direction, the modulus is going to be very high in that direction, but very weak, or the part's going to be very weak in the transverse and out of plane directions. So really, what we ultimately want is somewhere right in the middle here. We want the primary direction to be controlled so that we get a good modulus distribution, but we also want some amount of orientation in the opposite direction so that the modulus doesn't decrease more than what we would want. We want to be able to control all three directions if at all possible, with a particular focus on one of them.
Thank you for watching the Moldex3D Advanced Tips and Tricks. Please don't forget to leave a like on the video if you enjoyed the content. If you'd like to suggest a future topic, feel free to let us know down in the comments. And finally, if you want to see more content like this in the future, don't forget to subscribe to our YouTube channel.